we are. And I'm already sharing, so come here, Control L. And can somebody out in Zoom land confirm that you can see the slides?
Yes.
Yeah.
Perfect.
Yes. Excellent. All right. Without further ado, Jeff Lagarias.
Um, Somebody said we can't see the slide.
Oh.
Well, we can. Okay.
Me too.
Um, Thanks to Mel very much for the invitation. Thanks to Mel for organizing these workshops over so many years and making such a nice community. Uh, Due to Zoom problems, I can't figure out how to share my screen. So Kevin's going to turn the slides. So turn the slide, please. Okay, this is a survey talk on the Collatz problem with brief reports on recent progress and perspectives at the end. The title might more accurately replace progress with in progress. Next, the topics covered. This is an abbreviated version of a longer talk. Collatz problem and the original problem, the history, what's known about the Collatz iteration, some remarks on probabilistic models for the Collatz behavior, which allow you to guess how the function behaves. There are many generalizations of the Collatz problem. I will only do one. And then the new materials on recent progress and perspectives on 3x plus 1. And there's one slide on the current state of the Collatz problem, which you can guess. Next. The Collatz problem has three versions. They concern the iteration of any of the following function on the positive integers. The Collatz function multiply. If it's odd, you multiply by 3 and add 1. If it's even, you divide by 2. The 3x plus 1 function normalizes it. It multiplies by 3n plus 1 and divides by 2 if it's odd, and then divides by n over 2 if it's even. So the 3x plus 1 function behaves very nicely because it extends to the two adic integers and is a homomorphism on the two adic integers. And then there's an accelerated version of the Collatz function where when you only work on odd integers, and if it's odd, you multiply by 3 and add 1, and then you divide out all the powers of 2 to get another odd integer. That's sometimes called the Syracuse function. Next. The main conjecture asserts that if you start with any non-negative, any positive integer and iterate long enough, you will get to 1. If it's the Collatz function, you'll get then to a cycle that cycles between 1, 4, and 2. The 3n plus 1 x function speeded it up, so you get into a cycle that's just 1 and 2 because you divided out an extra 2, and the accelerated Collatz conjecture gets you just to 1, to a fixed point. Next. The origin. The Collatz conjecture is unsolved, and it's attributed to Collatz. He wrote various letters to different people. I've seen different numbers. The one he wrote me said that he invented another problem in 1932, which I would call the original Collatz problem. And in one of his later papers, he said he had certainly had explained the problem as early as 1952 to Professor Haase at the University of Hamburg. The original Collatz problem appeared in its own right as a SIAM review problem in 1963. So that's the earliest version I know of that's something that's in print. And the usual Collatz problem appeared in a paper of HSM Coxeter in 1970. And he gave a talk to the Australian Mass Society, and they had a paper in their side issue where he mentioned the problem as something that was circulating around. and he offered $50 for a proof. Maybe Canadian, maybe Australian dollars. And he offered $100 for a counterexample. Now the prizes are different. Next. So here is the original Collatz problem in two versions. It is a permutation of the integers. So it's easier to say it takes 3n to 2n. It takes 3n plus 1 to 4n minus 1. And it takes 3n plus 2 to 4n plus 1. And the inverse thing then takes integers mod 2 or 4 to integers mod 3. And you can check this as a permutation of the integers and that it's reflection symmetric. Next. So g of 1 is 1, g of 2 is 3, g of 3 is 2, g of 4 is 5, g of 5 is 7, g of 6 is 4, g of 7 is 9, 8 is 11, 9 is 6. So we get 3 cycles out of that, 1, 2, and 3, and 4, 5, 7, 9, 6. Then we come to 8. It appears that the orbit of 8 is infinite. And experimentally, people have run it forward to about 10 to the 200. You can run it backwards to about 10 to the 200 and decide, well, it's going to infinity. No one can prove it. Next. The probabilistic heuristics allow you to make a prediction for how it behaves. The forward orbits will grow at a geometric rate, which is about 1.05. And if you run it backwards, then the heuristics predict it will also go to infinity geometrically, but at a different rate, which is about 1.06066. So I think that's interesting, but what can we prove? Next slide. Let's propose some weaker conjectures. So a weak conjecture, which I tried to prove for a long time, is that every orbit of G has natural density 0. I really thought this problem might be in reach, so I invite you, if you've got a lot of time, to think about it. So here's a weaker conjecture. The desperately weak conjecture, there is no orbit of G that consists of a density 1 set of integers in the natural density set on the positive integers. And here's an even weaker conjecture. Show that the orbit of 8 does not consist of 8 plus all the other integers bigger than or equal to 10. Okay, I don't know how to do that either. At least you could disprove the super degenerate conjecture by finding another finite cycle, in which case, following Coxeter's example, I would pay you $100. The payment would only be made once. On infinitely many cycles, there's no. Next. Okay, now I would like to talk about the results, what's known about the conjecture. The first is numerical verifications. The initial steps, there are many theorems. Density, one set of inputs go downhill is one of the earlier results. You can ask in the reverse direction, how many integers can you provably get to 1, and what can you say about cycles? Next. It's now been numerically verified at least to 10 to the 21st power, which is a big computation, and reportedly has been double checked up to something times 10 to the 20th. Next. If you're describing the initial steps of the iteration, they're described by its forward orbits, O plus of n, C of n, C of C of n, form a linear chain, might end in a loop, a periodic orbit. But if you consider its backwards orbits, which are all the things that eventually iterate to n. Those backwards orbit have a tree structure because it's a 2-to-1 map for certain integers. And you'll get an infinite tree if the element n that you start with is not in a periodic orbit. Otherwise, you'll get a loop for the periodic orbit and a bunch of infinite trees coming off it. Next, I'm going to repeat some old stuff. So it's most convenient to deal with the 3x plus 1 function, because the basic thing that was observed by Terrace and Everett is if you look at these iterates mod 2, they give you a symbolic dynamics attached to the iteration pattern, which consists of the parity of each of the iterates. And of course, you need to know that parity in order to compute the next iterate, because it tells you to decide whether to use x over 2 or 3x plus 1 over 2. And their observation was that if you look at the first k iterates mod 2 in the complete period from 0 to 2 to the k minus 1, then you got every pattern of 0, 1 vectors exactly once. So I have it here for k equals 3, looking at mod 8. If you put in 0, you get 0, 0, 0. If you put in 1, you get 1, 0, 1. And the parities for 2, 2, 1, 2, 0, 1, 0, and so on. And 2 to the k minus 1 has the parity pattern of all ones, first k ones. So many people observed that. So if you plug in 2 to the k minus 1, the iteration will go uphill for the first k minus 1 steps. And it will be multiplying by 3 halves each time, so it'll get a lot bigger. Okay, next. That lemma shows that the pattern of the first k iterates behaves like k coin flips over the average from 1 to n to 2 to the k. And so on these coin flips, if you flip even, you divide by 2. So you multiply the number by 1/2. And if it's odd, you multiply by 3 halves. And 3 halves plus a smidgen. Okay, so if you iterate k times, what you get is sort of dominated by whether you're multiplying by 1/2 plus 3 halves, but there's this constant term that's coming in from the plus 1 that will gradually increase or decrease. So we assign a parity sequence to this thing. Next slide. So if we take k minus 1 steps and we have this parity sequence and they are coin flips, the coin flips have the binomial distribution. And the kth iterate looks like of t will be 3 to some power, which is the number of coin flips that are 1, divided by 2 to the k. And then there will be this smidgen left over for which you have a exact formula that is there may be a misprint there, but it should be 2 to the k rho k of n times a certain integer, which is a combination of powers of 2 and 3 written down there at the bottom, summation 3 to the j, 2 to the bj. So you get a nice family of integers to examine. This formula has the feature that the left-hand side is an integer, but the two pieces on the right-hand side, they aren't integers necessarily. They're dividing by 2 to the k. So you're getting rationals on the right-hand side. But for looking at the size, the left piece is the important piece. Go on. Next. And the size, at least for the initial iteration, is dominated by these 3 to the ak over 1 times 2 over 2 to the k. And that's a binomial coefficient. It's biased because 3 halves. So Terrace used this to show that most iterates go downhill because if you take a logarithm of everything, you're going to get a random walk that's a biased random walk, and it's biased to go downhill because on the average, on the average each step you expect to multiply by the square root of 3/4. So that's the reason the Collatz problem goes downhill. Next slide. Um, so the stopping time introduced by Terrace is the minimal k before you get the k theta at less than n. And if for k bigger than or equal to 4, there always were a stopping time, then you would be able to prove the Collatz problem by induction. It just goes downhill to something smaller, you repeat. Um, well, you can't prove that, but what you can prove is almost all integers have a stopping time, and you do this by analyzing the tail of the binomial distribution, because the numbers that are not going to go down below the initial value after k steps are the part of the binomial coefficient where the zeros and ones have a lot of ones, and the fraction of ones that's bad is uh, one. It's a log to the base 3 of 2, or 1 over log to the base 2 of 3, which is about 63%. And you it's well known how to estimate the tail of the binomial coefficient using it's the foundation of the theory of large deviations, and it's it's a fra it's a it's got a power savings. It's a power savings smaller than x. So it's if you look at the integers from 1 to x, it's x to the 0.95996 or something. Next slide, please. Well, you can repeat this probability distribution instead of just asking to go down to the original value, which is the stopping time. You can ask how far down can you push it for almost all integers. And the estimate you will get will be the median of that distribution has 50% coin flips. So you can push all the way down to 50%. And the numbers with 50% evens, 50% odds will decrease at this rate, the square root of 3/4, and you can do it for the first k steps. And you will drive x down to x to a constant, and that constant is 0.79248. And so the optimal result of this sort was written down by Collatz. Again, you can analyze the tail of the binomial distribution down to near half and get this constant. You ignore the additive shift. Anyway, the point is this bound used up all the initial randomness of the coin flips in the first k steps. And after you've done this iteration, you've taken the numbers from 1 to 2 to the k, and you've packed them all down into a smaller set that's of size 2 to the k times log 3 over log 4. So you would like to iterate this procedure. Presumably all the numbers down at the lower level have been hit a zillion times, and you will just be able to iterate this and prove natural density 1 for smaller exponents beta, smaller than log 3 over log 4. But it's difficult to do that rigorously because you don't know what numbers at the bottom level you actually hit for actual sure. You don't have control over that. So maybe things are conspiring to avoid this. So the result has not been improved until the end of this talk anyway. Next slide. The best result that's been proved on large decrease of Collatz function iterates are a result of Terry Tao in Forum Math Pi, which says in its simplest form, you can the number of integers below x that have well, that for any given n that you take a fixed epsilon, you can drive it below n to the epsilon, has logarithmic density 1. So the logarithmic density is, as we've, I think, already had in at least one talk, You weight things by 1 over n, and then you scale the whole sum by 1 over log n, provided the limit exists. So natural density 1 implies logarithmic density 1, but not vice versa. And the analysis um, uses the accelerated Collatz map, um, and it uses some three-adic things also. I'd like to say, next slide, his result is much stronger than what I said there, because his theorem for logarithmic density 1 is you only accept an integer if in its forward orbit it takes some value less than f of n, where f of n can be any non-decreasing function that runs off to infinity as n goes to infinity. So not only can you make it smaller than n to the epsilon, you can make it smaller than log n, or the inverse Ackermann function, or as is claimed, any function that grows so slowly to infinity that it is not provably computable. You know, fast-growing functions can be difficult to compute, but apparently slow-growing functions also. Um, so this result sounds so strong that you would say, well, why doesn't that really make tremendous inroads into the problem, like finitely many cycles or non-existence of an orbit that runs off to infinity? But in fact, um, there's a question from does the rate at which f of n goes to infinity matter? Um, the theorem, as stated, has quantifiers. You're given your f of n in advance, and then the theorem is that the resulting set of n's that beat this bound, which has logarithmic density 1, which is an asymptotic limit. So it's a new theorem for each f of n. Ask me again in the question period. Go on. Okay. What if you say I don't want to know how many integers get very small. I want to know how many integers actually get to 1. So the conjecture is at least a positive fraction of integers ought to get to 1. There is a three-adic system of functional equations for analyzing this problem. And in a paper in 2003, it's a system of difference equations. There's one for each power of 3. This exponent 0.841 was gotten by going to depth 3 to the 11th. And if you go to higher depth trees, and there's an eigenvalue equation to get that constant x to get the exponent, and the exponent appears to be going to 1. So it would be nice to prove x to the 1 minus epsilon, but that's still an open problem. Next slide. Okay, the conjecture about periodic orbits, the most natural conjecture is to conjecture there are only finitely many cycles. The fact that there's a unique cycle in the positive integers seems coincidental, whereas finite cycles may be structural. And indeed, if you look on the negative integers and you think that you're going decreasing in absolute value, then there will have to be cycles, and there are 3 known cycles: -1, -5, -7, and that's a misprint for -10, and then a cycle beginning with -17. I think I saw one paper recently that was asserting that numerical calculations sort of indicated that about one-third of the integers each were going to the 3 cycles. No, maybe I have that wrong. Let's go on. But one thing you can prove if you look at cycles of length k is that immediately you can prove there are at most 2 to the k cycles of a given period k, because for each period k, you can label the upward and downward movement inside the cycle by the parity sequence. And there are only 2 to the k parity sequences. And so you can write down the series of compositions of functions to get that period. And everything is linear. So you will get a linear equation for determining that cycle, and the putative cycle will be a rational number. Um, okay, and if that rational number is an integer, then it could be conceivably a 3x plus 1 cycle, but you would have to plug it back in and iterate it to make sure, because um, well, I'm not absolutely sure this that it's going to actually produce the same symbol sequence as the symbol sequence you use to compute the cycle. But anyway, it's a theorem for the function t that will happen if it's a rational solution. And these rational solutions you get, they have an odd denominator, so they are two-adic integers. So the 3x plus 1 recursion makes sense for them. So you can actually iterate these things for the odd integers. And the theorem there, which is possibly on the next slide, um, um, it's not, but there is a theorem that says it will indeed always match the symbolic dynamics of iterating the rational thing you find will match the symbolic dynamics of um, what you had. That's a theorem for the function t of x, but it fails for Collatz function c of x. So there was something to prove. Next slide. What's known about cycles? There are some theorems proving that let's say, there are infinitely large set of possible symbolic dynamics where you can analyze. You can find all the integer cycles, and these typically use Baker's method and transcendence theorem. And the strongest theorem of that sort that I know of is the theorem of Brock's, which says if you look at a symbol sequence for a cycle, which is zeros and ones, and a descent will count only the blocks of consecutive zeros. So instead of counting the zeros separately, I group them into blocks of separate zeros. If there are not very many blocks, then you can effectively compute an upper bound on the cycle size and find them. And that works up to 2 log the length of the cycle. So in particular, for the original cycle, if you have the case where there's all 1, 1, 1, 1, 1, and then a single, and the 1, 1, 1, 1, 1 actually hits a 2 to the k, hits a power of 2 at the last step, then you have only one descent, and that was done earlier by Baker's method. Next slide. Another theorem along these ways are if you restrict to the cycles of period k, again, the Baker's method allows you to show you can't get anything close to the bound 2 to the k. You can get that the number of cycles of length k is k to a constant. And this applies more generally to the 3x plus d map, which I will come to. Next slide. There's a way to actually empirically rule out the existence of cycles, and the basic method is due to Crandall, and it uses facts about the continued fraction expansion of log to the base 2 over 3, because there's a formula for a periodic orbit, and it has a power of 2 minus a power of 3 in the denominator, and you're going to do best when the power of 2 and the power of 3 are nearly canceling each other out, and that will favor periods that are close to convergence of the continued fraction expansion. But his theorem is that um, you can get a lower bound that's roughly like the square root of k that will show that the minimal element in a period cycle of period 3 is bigger than the two convergence near the middle of the continued fraction of size around k. And so by using this bound, if you've proved the 3x plus 1 conjecture up to some bound, then you can eliminate small cycles. Um, um, so I would say that cycles up to uh, 275,000 squared can probably be eliminated at this point. Next slide. Um, the stochastic models for the 3x plus 1 map. You can study this probabilistic model that says that trajectories appear to behave like a logarithm of the size of the number behaves like a random walk with a drift, um, and make predictions. It says that most for the 3x plus 1 map, the random walk calculation will say the expected number of steps um, until you get to 1 from a given n should be around 6.9 times log n, and then the central limit theorem will make it have some tail distribution around that. Next slide. Um, we use this random walk model with large deviations to make a prediction how large what's the slowest rate of speed with which you get to 1. So apparently all the iterates go to 1 at a geometric rate, which is why anybody who puts this problem on the computer says, why isn't this easy to prove? Because everything is decreasing exponentially fast. And it makes a prediction that the worst case of the rate will be a constant, which is about 41.67 times log n. And at this point, I don't think any trajectory has been observed that requires more than 37 times log n to get to 1, because the probabilities of observing these extreme events also decrease exponentially, and so you can fit the large deviations model to make a prediction how likely you are to see an event, for example, um, that you see a particular starting point that has rate that takes 37 log n. And the answer is the probability of it is something like 10 to the minus 20. So it's not surprising if you haven't seen it. Okay, next slide. Um, there's another statistic you can ask, well, how big can you get from the starting point? So I start at n, and this example with 2 to the n goes 2 to the k minus 1, iterates to 3 to the k minus 1, allows you to say that there exists infinitely many n's such that you iterate them, you will get to a number of size n to the 1.585. And maybe you'll go to 0 later on, but you will go uphill for a while and you can get to n to a strict power bigger than 1. And the probabilistic model allows you to predict what is the extreme constant you're going to see, and it's n squared. Next slide. So here's an old picture from some of the data. So the large deviations model on a logarithmic plot also say the way you will get to get to this optimal value of n squared is you will go uphill with one slope for about 9 log n steps, and then you will go downhill with another slope to about 22 log n. And this is the plot of the extremal values that were found up to 10 to the 11th. There are better plots of this sort. I believe at current things up to 10 to the 20th, they never saw anything that got bigger than 8n squared. Um, um, so anyway, the probabilistic models seem to accurately predict what the thing is doing. Next slide. Okay, there's a nice generalization to the two-adic integers. The map is ergodic, strongly mixing, and so on. I'd like to say something about the 3x plus d maps where we replace 3x plus 1 with 3x plus d, where d is relatively prime to 2 and 3. There's an interesting example where you do a real extension of the 3x plus 1 problem, which shows some of these theorems on symbolic dynamics and going downhill hold more generally, and they hold in situations where bad stuff can also happen. So the bad stuff is not can occur. And then finally, Conway at the beginning of the subject showed that you can make a generalization of this map that's piecewise linear in a bunch of congruence classes, such that the iteration problem of deciding whether it um, in his case gets to a fixed integer is undecidable because you build the halting problem into it. Next slide. I'm going to say something about the 3x plus d problem. This was the theorem. It says the 2 to the k solutions all occur with a rational value. And if you clear out the denominators of these rational cycles for 3x plus 1, you will get an integer cycle for the 3x plus d problem where d is the denominator that you cleared out. And as I said, the surprising point in the proof is that the solution of linear equations actually then, when iterated, has the same symbolic dynamics. So that a putative rational solution is an actual rational solution. Next slide. You get a bound on cycles. The transcendence theory result applies to give the same bound. I'd like to say that what we can prove in this problem, typically if it can be proved for 3x plus 1, the general results we have can also be made to work for 3x plus d as well. Next slide. The interesting thing that's new when you vary 3x plus d is you can now vary d, and some d will have a lot of periodic orbits, but you get a new problem, and the new problem, and this is a theorem where you show that there's some d that have almost d independent periodic solutions, and then there are others that don't seem to have many. Next slide. But the 3x plus d map has the same probabilistic heuristics, so everything should go downhill. So there should be at least one cycle, because where are the integers going to go? I don't know how to prove that. It's a really elegant, nice problem. I'd like to explain why it's hard. You have a formula for this rational number. The formula expresses it with a numerator and a denominator, and the denominator is a power of 2 minus a power of 3. And so that's a large number going to infinity generally, which is a theorem. And then something in the numerator has to cancel out the stuff in the denominator. We don't know how to prove that. Next. Okay, now I come to the new result. So there's one good new result due to Goncalves, Greenfeld, and Madrid. This takes the tau proof and it extends the tau proof to a large family of maps that have the same behavior of expectedly going downhill. So they're either going to multiply by Q and add a constant for most residue classes mod P. And if you take the zero residue class, you divide by P. And you choose the residue class. The map has to have the property that for the residue class is mod p. The constant you subtract off always makes the resulting integer 0 mod p, so that it will go to the next. It will go to the other step. And here p and q are required to be relatively prime, but they need not be prime numbers. So anyway, the Collatz map is a special case of this, and the 3x plus d maps are special cases of this setup. And they had to strengthen and sharpen the tile proof to do that, in particular black boxing a probabilistic part of it. There's a probabilistic theorem input in there. I mean, it's a theorem, so the same behavior occurs for them. You can iterate down to a small number. And you use the bound q is less than p to the p minus 1. That's the threshold that says that going downhill is beating and going uphill. So if q is bigger than p times p minus 1, we expect there are divergent orbits, and we can't prove it. Next. Now I want to talk about recent in-progress results. So this is a paper that's on the archive that is in peer review somewhere. And this paper asserts to show the theorem that tk to the n less than n to the epsilon occurs with natural density 1. So this is a natural density result, which is the gold standard, as opposed to the logarithmic density 1 result. And it has apparently a mechanism to allow to iterate the Korek bound down to x to the epsilon. And it's got combinatorial ideas, which I want to have in the next slides. So the idea of this is that to prove density 1, you try to prove an even stronger result, which is that it's more like a Schnirelmann density. It says that the partial sums are bigger than 1 over a constant times n to the d. So it allows a polynomial decay, and it allows an arbitrarily large constant c at the beginning. But the requirement is that this kind of form of density must hold for all n bigger than or equal to 1. You can call a number as having a star density if it has a CD density for some values of C and D. Anyway, it's easy to show that a positive star density implies natural density 1, but the converse is not true. But what this extra definition of density does for you is it's closed under union and intersection and removing finite many things and various combinatorial operations in which the constants C and D are changing in explicit ways. And it's this combinatorial stuff that's getting used. Next slide. And in particular, this is a little hard to observe, but it is sort of one of the main things. If you take a set with D density, so his main theorem is going to be that the hypothesis, if you plug into this process a number with a star density, then some of its iterates will preserve a star density if the constants are chosen properly. If you take a number with a star density and you look at the numbers m such that m times 3 to the k plus I is in the set simultaneously for all the small exponents k and all the I in a range from 0 to k times 3 to the k. So if you take k equals 10, you're covering the full congruence classes mod 3 to the k 10 times. So it's a Ramsey type thing. It says, and you take all those m will themselves have a star density with provided they constants obey something. And another thing you can do is you can handle integer parts and get that sets that have 3 to a power over 2 to the power times n and rounding down, then you will still preserve a density. So those are some of the ingredients that are going in to try to allow you to iterate the Collatz result, the next thing that you can preserve the arithmetic structure in the interval. Okay, next slide. Okay, now this comes back to Terry Tao's thing. Why doesn't Terry Tao's 2022 result eliminate cycles or orbits that go off to infinity? Divergent orbit. So here's an answer I would like to give to that. So let's take a function we're iterating on n, and let's divide all of its elements into initial elements, which you may think of as elements whose iterates are going to go downhill, and final elements whose iterates are going to go uphill. And really, we have to classify the final elements. So the first definition is an input is strictly final if its forward orbit is uphill, meaning all of its iterates of n are bigger than or equal to n out to infinity. And this definition has to do only with the single forward orbit. Okay, you start in your orbit, you go down to eventually you'll hit the minimum value you're hitting on the orbit, and then everything after that will be a final element. Well, the definition of final is it's going to be in the forward orbit of a strictly finite final element. And this definition is global. So when you take a single orbit, you run down to the minimal value will be a strictly final element, and everything after it will be final. You get if you like, a certificate for that, assuming you can recognize a minimal element. And the initial elements will be everything left over. Next slide. Okay. It's not obvious that you can deal with strictly final in terms of computability, namely, how can you effectively compute if a number is strictly final? But it does turn out this is all computable if all the forward orbits go into periodic orbits. And indeed, you could prove a computational result that if you have an oracle that recognizes strictly final and gives you a yes or no answer, together with a generator for the thing, then there's an effective procedure to determine whether elements are initial or final. Next slide. So the main result I wanted to say on this subject, it's in process, although if you like it's an elementary consequence of a large deviation thing. It says, for the Collatz function C of n, there's a constant lambda such that the set of final elements below x has cardinality at most x to the 1 minus lambda for sufficiently large x. So it says that the set of final elements up to any value x is a exponentially small fraction of all the elements. It's got it behaves like it has fractional dimension less than 1. And in this theorem, the value you get for 1 minus lambda is about 0.9654, which is related to those extreme trajectories of length 41.677 times log n. The rate equations you solve give the same constant. And the strictly final elements, you can prove they're up to x. There's at most 0.94991. That is the constant that corresponded to the stopping sign. So you see there the density of the strictly final elements is less than the density of the amount you can prove for final elements. Next slide. Okay, so what I wanted to say having to do with where we are in the problem, every integer in the Collatz iteration in its forward orbit spends a finite amount of time visiting initial elements, then it hits the lowest point in its orbit, and it spends an infinite amount of time inside the final set. But nevertheless, if you look at all the integers, most integers up to x are going to be labeled initial. They're going to be labeled x minus a tiny fraction. And the main proof results on the Collatz problem concern the behavior of the Collatz iteration on the initial elements. They go downhill a lot. And there are very few proof results on the final set. The only results that I know that are proved are the results eliminating certain patterns of periodic orbits using the Baker's method. Next slide. The final slide. The current state of the problem is existence of cycles, number of cycles, existence of divergent trajectories. They're all open problems. As far as we know, there could still be infinitely many different periodic orbits for the Collatz function. There could be infinitely many functionally independent divergent trajectories. And indeed, we think the second thing happens for the original Collatz problem, the Collatz permutation. The guess there is there are infinitely many divergent trajectories, all very thin. And then Tao's results do not rule out either one or two. Next slide. Thank you.
All right. Wow. Are there any questions for Jeff? Carl?
The original Collatz permutation.
Does Tao's proof apply to the original Collatz permutation? Carl Pomerantz asks.
No. Basically, the Tao method works on things. It doesn't work on things where there can be a divergent behavior. So you could ask, what would Tao's method do on the 5x plus 1 problem? So on the 5x plus 1 problem, which, by the way, does have a cycle that goes to 1, the heuristics say that there's a sort of a x to the delta set of a very thin set of numbers that will go to 1, and then everything else will go to infinity with the amount of things that will run off to infinity will be sort of like what's in this Inselman thing. It'll be 1 minus a constant over n to some power. That's what we believe happens. I wondered what you could do with the Tao method if you say, well, if you can't prove things run off to infinity, but maybe you can prove they get very, very, very large. But I can't say for sure about anybody's method, but my impression is you can't do that at this point. I think it's an interesting question what these methods will give about proving for things that are supposedly have divergent elements. How much can you prove they do grow from the initial starting point and to a power? That might be an accessible problem.
More questions? Also open to people in Zoom land. All right. Thank you very much, Jeff. Let's thank Jeff again. And our next speaker, Al Nathanson, starts in a few minutes. Second.